So we're starting a new unit, Virtual Physical Science. This unit is going to be all about electricity, and it's based on Chapter 7 in your textbook. So in Tana now it's becoming wintertime, and the air is getting drier, and if we all go back there, we may find ourselves one day getting zapped. Maybe after walking across the carpet in our sneakers, and then touching the door handle, or maybe after sliding over the car seat to get out of the car, and then touching the door. So what's going on there? Why does that happen? What causes it? And why is this equation true? Why do balloons plus hair equal fun? But you don't know what I'm talking about? Let me show you what I mean. If the air isn't too humid where you are, and you have a balloon, try this. It actually works pretty easily for most people's hair. If you rub the balloon on your hair and then you hold it next to your head, you should see your hair stand up just like it does for this girl. It's pretty cool. Give it a shot. Of course, the answer to both of those mysteries is electricity. Electricity is what's happening when we get zapped by touching the door handle or the car door, and it's electricity that makes balloons and hair equal fun. Electricity powers our lights and our computers, etc., anything electronic. It turns out that your heart is actually signaled by electrical signals to pump your blood throughout your body. Your muscles also receive electrical signals that tell them to contract or to release. And your brain is a big network of electrical signals passing in very complicated networks. So there's a lot of electricity going on all around us. Atoms, which as you know make up everything that you can see and touch, atoms are held together by electricity. The negatively charged electrons and positively charged protons hold each other together, and this is what gives matter its substance. Also, the electrons in the atoms of your feet and the electrons in the atoms of the floor you're standing on repel each other, and this is what gives matter the illusion of being solid. Because actually, most of an atom is empty space, and the particles in your feet and the floor could easily pass through each other if it weren't for the electrical repulsion between the electrons in those atoms. So we have electricity to thank for lots of things. Anything from atoms being held together, to you not falling through the floor, to your body working properly and having fun with a little bit of electrical charge on a balloon. So here's a little drawing of an atom. In my drawing, the black balls represent neutrons with no charge. The green ones represent protons, which are positively charged. And the little red things outside the nucleus are supposed to be the electrons. They have a negative charge. Well, as we know from last semester, atoms are neutral. That means they have to have the same number of positive and negative charges, the same number of protons and electrons. And this atom I've drawn has 5 protons and 5 electrons, so it has 5 positive charges and 5 negative charges, which makes it neutral. Electrons, because they're on the outside of the atom and not bound in the dense nucleus, are much more easily able to move around, and it turns out that it's usually electrons that make electricity happen. The protons, which are bound tightly into the nucleus, they have an electrical charge as well, but they can't really move around very much. They're not very mobile, and so usually protons aren't responsible for electrical phenomena. So some materials happen to be able to hold on to their electrons better than other materials. Let me give you an example. Rubber, which is what balloons are made of, is really good at holding on to extra electrons, and hair is not so good. And so you can imagine what happens when you rub a piece of rubber like a balloon onto some hair. Here's a diagram to illustrate what happened with that girl and the balloon. The balloon is made out of atoms, and so is her hair. And so both these things are neutral. They have many, many, many atoms in them, and I can't even begin to count them or draw them all. But just to illustrate the point, let's say there are 6 positive and 6 negative charges on the balloon. So 6 plus and 6 minus make 0, neutral. And the same is true of the hair. It's also neutral. And there are 24 charges total, 12 positive and 12 negative. Now if we rub the balloon on the hair, some of the electrons in the hair are going to be stolen by the atoms in the balloon, who happen to be much more attractive for electrons. So the balloon ends up with an excess of negative charge. Now the balloon has 6 positive charges like it did before. The protons aren't really able to move around much. But it's picked up 3 extra electrons excuse me, for a total of 9. And so it has a total charge of 3 negatives, because the negatives were more numerous than the positives. The hair, on the other hand, has lost 3 negatives, and so it has 6 positives and 3 negatives. It has 3 extra positive charges, and so it becomes positively charged. The balloon is negatively charged. But notice something important. The total number of charges is still 24. There are still 12 positive charges and still 12 negative charges. The total charge is conserved. The number of positive charges is conserved. The number of negative charges is conserved. This is just like conservation of energy. Charges can move around, but they can't be created or destroyed. Okay, so charge, like mass and energy, is conserved. So, with a negatively charged balloon and a positively charged piece of hair, what happens is that those opposite charges attract each other. So if she's holding onto the balloon and she holds it near her hair, the positively charged hair is attracted towards the negatively charged balloon. And that's one of the most important principles of electricity. Opposites attract. So we learned that electrical charge is conserved, just like mass and energy, and that opposites attract, meaning a negative charge and a positive charge will feel a force pulling them together. Now this is kind of a strange and mysterious force. Just like gravity, it acts without anything ever touching anything else. When you see something fall toward the ground, the earth is pulling it downward even though there's nothing touching it. It's kind of a force field that exists, that's invisible. And the same thing is true with electricity. Near anything that has an electrical charge, there's an invisible force field called an electric field in the area surrounding that charge. Here's an example of what the force field around a negative charge would look like. The length of the black arrows represent the strength of the force that you would feel if you were there, and the direction tell you which way you would be pushed. Electric field lines are always drawn for the force that a positive charge would feel if it was in that location. So a positive charge very close to this negative charge would feel a strong force towards it, and a positive charge farther away would feel a smaller force towards that negative charge. The idea of field lines was invented by a man named Michael Faraday, who wasn't very well trained in mathematics, but he was very imaginative, and he visualized these force field lines existing all around electrically charged things in space. At first people thought he was kind of nuts, but eventually his idea really caught on, and now it's used in any science textbook that you find talking about electrical charge. So that's what an electric field looks like around a negative charge. But what about around a positive charge? And what happens if 2 positive charges are brought together? We know that a positive and a negative attract each other. Well, it turns out that 2 positives push each other away. Opposites attract, likes repel. That means that 2 positives would push away from each other, and 2 negatives push away from each other. So here's what an electric field around a positive charge would look like. Since electric field lines are always drawn as the force that a positive charge would feel, all of these lines are pushing away, because if you put a positive charge anywhere near this positive charge, it would be pushed away. And just like in the other diagram, the lines get shorter as you move farther away because the force gets weaker. Just like gravity. If the moon was moved farther away from the Earth, the gravitational force pulling it toward the Earth would be reduced. Electrical forces also decrease with distance, just like gravitational forces. Alright, so in part 2 you're going to learn more about different aspects of electricity. I'll see you there.